Hello everyone, we are from Computational Thinking 01 from Group 1 and we are here today to present a study case for the final project. These are our group members, there's Jack, Shannon, Keiko and Amara. For the study case overview, the background is how are we going to manage a warehouse's inventory efficiently without leading to overstocking, stockouts and increased operational costs. We would want to optimize inventory levels and streamline the restocking process. And the problem statement would be design a computational solution in order to optimize inventory management. And the goal is to create a program that would be able to manage the inventory better, or overall better to optimize it. And this next would be the overview of the flow chart. So this flow chart is the short overview or overall on how we are going to plan the whole program without delving into much of the smaller details. So we see there's start to initiate warehouse system to set up the products. Then we will be setting up the supplies by inputting the details and record costs. And then we would set out the warehouse capacity. And then we would allocate stock using greedy algorithm and then check the reorder needs using binary search. And then check the reorder needs using binary search and check sales history using threshold, flag products needing the reorders, and then calculate robot route using the grid algorithm. The next would be select suppliers using brute force, and the next would be the output, which would display the results. The stock allocation, reorder recommendation, robot route, and supply selection. And then the flowchart would end. Next. And these are the four detailed sections of the flowchart. There are four. The first is demand prediction using binary search. The second is find how to optimize the stock by using the greedy algorithm. The third is robot routing using greedy algorithm. And the fourth is finding the best supplier combinations using brute force. Next.
And then we're gonna use binary search for demand predictions. Its purpose itself is to predict whether to pre-order based on historical sales data. And how it works is basically we will sort sales data and compare against a threshold using binary search. If threshold is reached, pre-order is needed. As we see the code rundown over here defines a method needs reorder, product underscore ID, which is the product we are checking, and threshold, which is the sales number. And then if product underscore ID is the product doesn't exist in the dictionary, we can process. We return false over here. Sales data, we will sort all the data. Left, right is to initialize the pointers of the binary search, while left and right here is if the search space is valid, compute the middle index. And if the middle value equals to the threshold, we will found it. And if data over here, we will move the search window. If the mid value is smaller than threshold, we will go right. But if it's larger, we will go left and then return to false. If we finish the loop without finding the threshold, we will return false. Next, please.
Okay, so the second part is finding how to optimize the stock using the greedy algorithm method. This is basically used to optimize the warehouse space by prioritizing the high demand products. So what is inputted in here using, so we've defined the function as allocate underscore stock. It is to allocate products to warehouse using the greedy algorithm where we input the number of products with its priority and also its size. So what the algorithm does is that it allocates the stock based on based on the maximum capacity of the warehouse itself. So the products that will be allocated inside the warehouse itself would be the products that are high in demand because they're high in priority and they also fit the size inside the warehouse itself. That's why the function in itself takes in the products, it puts it in a list, and it depends the attributes, which is the priority and the size, and then it sorts it in descending order, and then it allocates it into the warehouse according to the maximum capacity of the warehouse itself. This is the flowchart, the pseudocode, and this is the actual code.
The third part of the algorithm would be robot routing by using the greedy algorithm method. The grading algorithm method of the robot routing is minimizing the robot travel distance for the order fulfillment. So we are going to compute the shortest travel distance for the robot routing to ensure the delivery speed so that it wouldn't be taking too long. So how it works based on the flowchart and the code is we are going to start at the robot's current position and then the robot would always pick up the nearest unvisited order and then repeat until all orders are fulfilled. And next.
Okay, next we have finding best supplier combinations using brute force. Okay, so in large warehouses, supplier selection is critical because it impacts both cost and delivery speed. But with multiple suppliers offering different prices and lead times, how do we find the best combination? So we can use brute force, which is a method that guarantees the optimal solution by evaluating every possible options. So how does it work? First, we need to input data, which is to start with supplier details, cost, and lead times. And then we generate the combinations. So the system checks every possible way to combine suppliers, for example, single, pairs, triples, etc. And then we filter valid options. So the only combinations meeting the warehouse maximum lead time survive. And then lastly, we pick the winner. From the valid options, we select the lowest cost combination. Okay, so the code uses Python's combination to generate possibilities for each combo. It calculates the total cost, which is the sum of supplier costs and max lead time, which is the slowest supplier in the combo. If a combo meets lead time constraints and is cheaper than previous options, it is safe as the new best. This is the code. So why do we use the brute force? We use brute force because brute force is like checking every route on the map to find the shortest one. It's 100% accurate but can be slow for huge datasets. This is perfect for warehouses with a manageable number of suppliers. The pros is it guarantees the cheapest valid solution and it has no complex math. But the con is it is not scalable for hundreds of suppliers because it will result in combinatorial explosion.
Okay, so obviously we explain about all of the algorithm. In here, we will conduct all the algorithm into one workflow only. So here, set up products, we will input all the products details, and then we're gonna set up all the suppliers, which we will enter all the supplier informations. And then thirdly, we're gonna set warehouse capacity. In here, we will define all the total space available in the warehouse. And then in here, the system will print all of the entered data so that the user can verify it before running the further process. Okay, next please. And then over here, the system will try to fill the warehouse as many high priority products as possible. But if nothing fits, it will tell the user. And then we will check for the orders in here. The users will enter a number in threshold, and the system prints whether each product needs restocking or not. And then here, robot rerouting is basically the user sets the robot starting point and order locations. It will print the path of the robot should take. And lastly, the supplier selection over here, the user will set the max allowed delivery time. If found, it shows the supplier's total costs, and if not, it will tell the user. Jack.
Now that we've seen how the system works, let's look at a real output example to understand how it all comes together. This is the result of running our warehouse management program with sample data. Okay, let's dissect this step by step. First, there's the input summary. The warehouse capacity is set to 1,000 meters squared, and there are 3 products loaded. First is laptop, then calculator, and lastly desk. The 3 suppliers are registered with varying costs and lead times. And then there's stock allocation. The system allocates 99 units of laptop, prioritizing it due to high demand and small size. This gets 0 units, and its large size makes it impractical given warehouse constraints. Then we have reorder alerts. The system checks if sales exceed the reorder threshold. The result calculator needs restocking, but laptop and disk are safe. And then there's a robot routing. The robot starts at position 0. It plans the shortest path for orders at location 3, 4, 5, 9, and 10. And lastly, there's supplier selection. With a max lead time of 40 days, the cheapest valid option is Cookie Express. Even though its lead time is longer, it's the only supplier within the cost and time constraints. Why does this matter? Because it is efficient in terms of space. The system maximizes warehouse use by prioritizing small, high-demand items. It also picks suppliers strategically, even if lead times aren't ideal. And there are no human guesswork, just data-driven logic.
Okay, so now we move on to the actual code. This is the actual working of the code. Maybe to summarize this a bit. This is the same code that we have presented in the PowerPoint. This is just the actual version in the Google Colab itself. So we import iter tools from the module combinations. This is the class for the warehouse systems. This is all the self functions. This is the binary search function, the first function where we've defined needs underscore reorder to find the demand prediction. And then for the second algorithm, the greedy algorithm for stack allocation, this is the function. It's allocate underscore stock. The third algorithm for robot routing is this one. So in the previous project that we've done, we've used the Dijkstra's algorithm. However, we cannot use that one in the actual program because we don't have an actual map for the robot itself. We only have numbers. So next is the brute force function. It's select underscore suppliers. It's in this part. And then this is the main workflow. This is another definition for running the whole system. This is where we set up all of our products. We gain the input from the user, the name of the product, the priority, the size, and the number of sales of that product to gain the sales history. And then this is the second part. We want to gain input for the suppliers, where we would later compare all of the suppliers, and we'd find the best combination of suppliers from there. This is the third function is the warehouse capacity function. And then this is the fourth part where we would show the input summary. And then this is the fifth part, the result of the stock allocation function. The sixth part is to check for the reorders. The seventh part is for robot routing. The eighth part is for supplier selection. And then it would print out the output of that combination. So this is the output, but let's try out the actual program so we know how this works. So let us try. Okay. Enter number of products. Let's say it's 3. Product 1, laptop, for example. And then let's say it's at the 8th priority. It's very high. The size in meter square, let's say it's 0.00, let's say 0.01. The sales history, let's say 20, 30, 4. Okay. Product 2, chair. Priority 2, for example. And then the size is, let's say, 10. The sales data, 210, 0. Product 3, let's say toilet, 10 in priority. The size is 0.001. Sales, 200, 100, 500. Okay, number of suppliers. Let's say we have 2 suppliers. Supplier from Alibaba. No. Alabubu. And then the price is 3,000. And then the lead time is, let's say, 50 days. And then the second supplier, let's say it's Birdie Express. The cost is, let's say, 4,000. The days, 20 days. And then the warehouse capacity, let's say it's 1,000. This is the input summary where we have inputted the capacity as 1,000 meter cube, the products, the laptop, the chair, the toilet. This is the priority, the size, the sales history. These are the suppliers, the Alabubu, Birdie Express, and this is the stack allocation. The result of the stack allocation is that we need 999 toilets in the warehouse. So next we need to check for the reorder. Which product do we need to reorder, right? So let's say the threshold is 20. Okay, so no reorder is needed for the chair and the toilet, but we need to reorder the laptop because the stock is very low. The robot rerouting, let's say it starts from the position of 3, for example. The number of orders, let's say 5. The position of the first one, 3, second 5, 4, 7, 0. Okay, so it checks for which position is closest to the robot right now, which is 3. So it starts from 3 and then 4, 5, 7, and 0. Next, we need to enter the maximum allowed supplier lead time. So we've compared all of the suppliers. Some of them have 50 days, the other has 20 days. So let's say our maximum lead time is 30 days, for example. Okay, so the algorithm has chosen to use Birdie Express, which costs $4,000 and the lead time is 20 days. So this is the result of our program. These are more diagrams, flowcharts for each detail of the algorithm. And that's all from our presentation today. Thank you.
Thank you.
Thank you.